Now let's use the localized electron model to fully describe the bonding in a couple of molecules. I want to start with water. The first thing we have to do when we do a problem like this is draw the best possible Lewis structure we can for the compound. And water, of course, looks like this in its Lewis structure. Then we need to figure out what the substituent number and hybridization is on all of the atoms. And here, really, that only involves the central atom, which has a substituent number that's equal to 4. A substituent number of 4 is going to give me sp3 hybridization on the oxygen. So we can say that that oxygen is sp3 hybridized. So there's sp3 hybridization on the oxygen. Now, hydrogens only have one s orbital, so we don't ever have to worry about hybridization for hydrogen atoms because they only have the 1s atomic orbital, and there are no p orbitals to hybridize. So there should be 4 equivalent sp3 hybrid orbitals. Because whenever we have sp3 hybrids, there are going to be 4 of them. The superscripts in the orbital designation should add up to the number of orbitals that there are. Another way of saying that is that the substituent number is telling us how many hybrid orbitals we need. So there are 4 sp3 hybrid orbitals on oxygen. So let's draw what that would look like. Here's the oxygen, and I'm going to draw those sp3 hybrids as just big lobes like this. Just for simplicity, I'm going to draw a single lobe. So each of these little, this looks like a flower, each of these little blue petals that I drew is an sp3 hybrid orbital. So I'm going to label them. This is an sp3, this is an sp3, this is an sp3, and this is an sp3. These are my 4 sp3 hybrids. Of course, there are these other, there's another shrunken lobe on the other side, and I'm just leaving that out for simplicity's sake in my drawing. So in 2 of those sp3 hybrids, I'm going to have the lone pairs on my oxygen. So I'm going to have a lone pair residing in one of the sp3 hybrids and another lone pair residing in another of the sp3 hybrids. The remaining 2 sp3 hybrid orbitals are going to overlap with the 1s orbitals on hydrogen to create this single bond here and here. So let's draw what that would look like. Here I'm going to put my hydrogen atom, and here I'm going to put another hydrogen atom. And the 1s orbital on hydrogen is just a spherical atomic orbital. So I'm going to put my 1s orbital there. Now, hydrogen is going to bring 1 electron to the table, and oxygen is going to bring 1 electron to the table. So I can make a bond by having the oxygen and hydrogen share electrons. So that's just a classic covalent bond. So there are 4 sp3 hybrid orbitals on the oxygen. 2 of them are going to overlap with hydrogen 1s orbitals to form covalent bonds or single bonds. And so the other 2 sp3 hybrid orbitals house lone pairs on the oxygen. So they're in both pictures and words. I fully described the bonding in the water model. You'll notice that the substituent number of 4 also gives the molecular geometry of the water molecule, right? It tells us that it's going to be a bent molecule with bond angles less than 109.5. So this is going to be what the water molecule